Yeah, good evening all. Hope you can hear me. So first I'll introduce myself. I'm Nidhi Chaudhary and I'm working as the new energy leader for Emerson in India. Total 2 decades of experience in power, utilities and energy. So this session is on waste to energy portfolio which each of the industries have. And it's a pleasure to welcome to waste to energy session which is very important and critical for India's acceleration towards the new energy era, because it not only caters to the requirement of energy that our country needs in-house, as well as it manages the waste which is a nuisance to the country. So let me start calling to the participants. So our first presenter is Mr. Shashi Shekhar. He is the Chief Manager, Corporate Petrochemical GAIL India Limited. He has a total experience of around 13 years and a natural gas distribution expert for NCR region, operations and maintenance of gas processing units in Kandahar. So welcome Mr. Shekhar for the presentation.
Good afternoon everyone. Today my presentation is on biopolymer production from agriculture waste through bio-methanol. As we know, we are facing the global problem due to pollution. As per the emission due to plastics wastage, we are getting 2.24 gigatons of CO2 equivalent, and that is equivalent to 5.3% of the global greenhouse gas emission. And we know the polymer fragments are converted in microplastic. It takes huge times and decade. Now we having two problems. One is the tackling with the pollution problem of the polymers. Second one is how we handle the agriculture waste, that is mainly due to mainly from the corn, wheat and rice husk. That is approximately 115 billion tons. We having the problem of tackling of 115 billion ton of agriculture waste. Then we have a solution to convert this agriculture waste in biomethanol and then process this. We use this biomethanol as a bridge to convert in the PHA for the biopolymer production. This is the difference between the traditional convention for polymer production and the biopolymer production. Traditional biopolymer production, it is not non-reversible and it takes huge time to convert into the landfills. But in the biopolymers, it will convert it into the natural ingredients of the earth within 50 to 60 days. The first generation biopolymers is mainly based on the food grains, and the difference between first and second is based on the agriculture wastage, mainly the cellulosic biomass. The steps in this process we take, the first is the segregation of feed stocks, then conversion of this feed stock in the biomethanol, then biomethanol through the biomethanol into the through the route of syngas, and finally the PHA and then the biopolymers. The first step for the conversion of converting is the pre-treatment and hydrolysis of the lignocellulose to convert this agriculture waste into glucose and xylose kind of material, and then we chemically can convert this into the methanol at the temperature of 700 to 1100 degrees Celsius. Through the chemical gasification, we convert this lignocellulose in CO, H2 and CO2, and then chemical conversion in the presence of copper, zinc oxide and Al2O3, we convert this syngas in methanol. This is the diagram through which we convert the methanol from the agriculture waste. Next, this is the microbial synthesis of PHAs. The methanol is, as methanol in the microbial synthesis of PHA, the methanol is entering in the biodegradation in process using the Caprivius nectar bacteria that convert in the formaldehyde, then formic acid, then convert into CO2, the reducing power, then biosynthesis, and the acetylic CoA, and then polymerization, then finally convert into PHA. Now this process having less efficiency, so we have to increase the efficiency of this process using the metabolic engineering that increase the 45% of PHA levels, and second one is from the unmodified strain to using engineered E. coli bacteria. It will increase the yield strength from 3.2 gram per liter to 6.8 gram per liter. Third one is increase the carbon efficiency from 0.12 gram per gram to 0.25 gram to gram. It increase the efficiency of approximately 108% of total. Now here we use the co-cultures of the advanced recovery to increase the efficiency of bacterial fermentation. Here we use one bacteria, Bacillus, with the Coprovisus to increase the synthetic efficiency of 1.7 times faster. It increased the higher PHA conversion, approximately 62%, and the second one is the cost impact that decreased approximately 30% of the cost of the conversion. This is the differentiation between the metabolic engineering and co-culture synthesis. For first one, as we know, the dissolving fatty acid through the Pseudomonas bacteria that increase the PHA level by 45%. Second is redirecting the metabolic engineering with the E. coli is achieved the 108% of its improvement from 0.12 to 0.25 gram PHA per gram of substrate. Third one, rewriting the metabolic engineering in E. coli booster that increased the yield from 3.2 to 6.8 gram per liter. In co-culture, along with the other bacteria, it increased the 1.7% the speed of the reaction and increased the PHA yield by 62%. Third one is CO2 cultures have improved overall the process economy by 18 to 25% and optimized the co-culture achievement stable PHA production by 8.3 gram per liters. And along with this, these are the some additional improvement. If we use the bioreactor designing with the aerations and the temperature control, it will increase the PHA efficiency 1.8% and CO2 evolution by 20%. And HCDC, high cell density cultivation, it increased the PHA extraction up to 70 gram per liter. This is the overall in 1 ton of agriculture waste. We get 60 kg of fermentable sugars, then 150 to 180 liter of biomethanol, and finally we get 80 to 100 kg of biopolymers. This is the comparison between the traditional biopolymers along with the traditional polymers. The substrate cost reduced approximately 85% because the conventional polymer production having substrate cost of 0.55 euro per kg. Second one, PHA yield 6 to 8 gram per liter, it increased 8 to 10. And third one is carbon efficiency, it increased 12 to 15% to 24 to 70%, almost more than 100%. Target of reduction of this production cost in the range of 1.2 to $1.5 per kg, which is for traditional bioplastic ranges is 1.3 to 2.0 kg per kg. The strength, the tensile strength for the biopolymers is almost similar to the traditional polyethylenes. Second one, the life cycle of this biopolymers, that is almost 50 to 65% weight lost within the 60 days. Now this is the cost comparison for the conventional petroplastics. Its cost approximately $1 per kg, and the biomethanol through 1G. It's approximately 1.1 to 1.5 G, and the present our 2G technology, it is ranging between 1.5 approximately. So we have target to reduce the bio-production cost in the range of 1.2 to 1.5 dollar per kg. And second one, the reduction in the environment impact by 40% approximately through the biopolymers that reduce the waste pollution due to the agriculture waste. And this radar graph that is showing the tensile strength, flexibility, thermal stability, durability, and barrier potential, that is almost equivalent to the traditional polymers with the biopolymers. This is the overall milestone structures that shows the we required some regional biorefineries to utilize this agriculture wastage to convert agriculture waste into biomethanol, then convert in the finally in the biopolymers. Second is the enhance in the bioprocessing technology through the enhancing the yield of the bacteria, which reduce the cost of the biopolymer production. Third one is the energy. We can utilize the solar or some renewable energy in this process to reduce the reduce the cost of this biopolymer production. Third one, the policy. We need support from government to reduce the cost through the carbon credits utilization, which will increase the efficiency of conversion of agriculture waste into the biopolymers. These are the references we have used in this presentation. Thank you.
Thank you, Shashi.
So let's come to the second session, which will be presented by Mr. Ketan Pednekar. Ketan ji is an expert in energy transition with over 25 years of experience, and he currently promotes energy transition technologies from Scotland, and he belongs to Scotland Development International, and he is presenting on tidal streams for India's clean energy.
Yeah, thank you very much. So, good afternoon, everyone. I'm Ketan Pednekar from Scottish Development International. We are a trade and investment agency of Government of Scotland, working across the international markets. Our role is to help Scottish companies expand globally and try to attract high quality inward investments into Scotland. So today I want to walk you through how tidal stream energy can become a meaningful part of India's clean energy future, and how Scotland's hands-on experience in this sector can help India accelerate its journey. This is a story about predictability, engineering maturity, and a renewable resource that India has not yet tapped. So here is the flow for the next few minutes. I will start with a quick overview of tidal stream energy, then look at the global landscape and the technologies that have matured over the past decade. From there, we will shift to India, its resource potential, cost trajectory, and where early projects make the most sense. And finally, I will close with applications, impacts, and a practical roadmap for moving from pilots to scale. Now, tidal stream systems harvest the kinetic energy of fast-moving tidal currents. We can imagine underwater wind turbines. And the key advantage is predictability. Tides follow the moon, so we can forecast the output years in advance with remarkable accuracy. For India, major hotspots are Gulf of Khambat, Gulf of Kutch, and parts of the Sundarbans. Now, Scotland has spent years building both the technology and policy frameworks for this sector, and that experience can significantly shorten India's learning curve. Now, globally, the sector has moved well beyond prototypes. Now we have multi-device arrays operating in real sea conditions, especially in Scotland and France, with pilots in North America and Asia as well. Each dot you see on the slide represents an operational or a long-running test site, which is a proof that it is no longer experimental. The lessons from all these deployments is consistent. Test in water, iterate quickly, and the costs fall. Standardized foundations, modular turbines, and streamlined maintenance are making the projects safer, faster, and more economical. When selecting a tidal stream site, hydrodynamics come first. Current speed, directionality, and depth. And here is an important point. Because the available power scales with the cube of water velocity, if the current speed doubles, the power potential increases roughly 8 times. That is why identifying genuinely fast flows is absolutely critical. And from there, we assess seabed conditions, environmental sensitivities, and proximity to the grid. On the engineering side, decisions around turbine type, foundation design, cable routing, and maintenance access shape the overall system and its cost. And the project development sequence is familiar like many other projects. First you do resource assessment, then concept design, environmental and social impact studies. Then you go for detailed engineering, installation, and once it is operational, you do the monitoring and maintenance. Now there are two dominant approaches today. One is seabed mounted turbines and floating platforms. Now seabed mounted systems are robust and are already proven in high flow environments. Floating platforms, on the other hand, simplify the installation and retrieval, which reduces the downtime and makes upgrades much easier. These options allow us to tailor solutions to Indian bathymetry, monsoon conditions, and available port infrastructure. We are also seeing innovations like larger rotors, shared moorings, tow port maintenance, all of which are helping to reduce the levelized cost of energy over the project's lifetime. Now, India's tidal opportunity is both real and environmentally concentrated. On the map, the larger bubbles, warmer colors, show where the watts per square meter are the highest, and that's where the earliest commercial scale arrays should be placed. The Gulf of Combat consistently shows fast currents at around 2.5 meter per second, giving roughly 2,600 watt per meter square of available kinetic energy. This is one of the strongest tidal resource zone in the entire region. Now, Gulf of Kutch reaches even higher peak flows, up to around 3 meter per second square, with about 4,500 watt per meter square of energy, available kinetic energy. It also has advantage of multiple channels and existing coastal infrastructure. So it makes a lot of sense to put a pilot there. Now, South Gujarat and West Coast states, Karnataka, Maharashtra, Kerala, see 1.5 to 2 meter per second flows, giving 500 to 1,300 watt per meter square, suitable for selective pilots, especially where the grid access is closer. On the east coast, velocities are much, much lower, zero point 0.8 to 1.5 meter per second. But the Sundarban and Hooghly stand out, reaching around 2 to 3 meter per second in some channels and providing around 2,600 watt per meter square. This zone is really ideal for microgrids because of its remote nature and resilience application rural electrification needs. Across all the regions, a past study estimated total tidal potential at around 12.46 gigawatts. But the immediate priority is not the headline number. It's where the early megawatts can be successfully deployed with highest certainty and value. Now the costs are falling as the deployments scale. UK trajectory shows LCOE approaching around 78 pounds per megawatt hour by 2035, roughly about 8 to 9 rupees per kilowatt hour, depending on the exchange rates. That's a bit on a higher side, but competitive for a predictable, grid-friendly, renewable resource, especially for a commercial client who is committed to net zero target. For India, the cost decline can really be accelerated through local manufacturing, shared infrastructure, and fleet operations across multiple sites. So each policy signal and offtake certainty will help suppliers invest and build local capability and encourage developers to place projects. Now, tidal stream complements solar and wind by filling predictable gaps, which makes it valuable for grid balancing. It is also ideal for coastal and island microgrids where diesel is expensive. Now, tidal streams don't eliminate the duck curve because the cycles don't match solar, but its predictability and partial phase offset can provide a firm renewable output during the periods where solar declines, supporting the grid and reducing the ramp challenge. Industrial users, ports, cold chains, desalination plants, and early green hydrogen plants, which are closer to the coast, benefit from this reliable, schedulable, renewable energy. And for the blue economy, dependable electricity supports fisheries, processing, and maritime services as well. Now, economically, tidal stream creates jobs in fabrications, marine services, cables, operations and maintenance. And Scotland's experience shows a strong supply chain multipliers as the projects scale. So environmentally also, the footprint is lower because the devices sit below the surface and operate quietly. And with a good site selection and monitoring, interactions with marine life can be managed responsibly. We can plan around fishing routes, sediment transports, and sensitive habitats with adaptive management already built in. Now, here is the practical de-risk pathway for India to move from potential to real tidal deployment. First is to start with engineering grade evidence, to carry out bankable resource and feasibility studies at priority sites covering the measurements, cable routes, bathymetry, environmental baselines, and port logistics. This will build confidence for investors as well as the government. We can deploy 1 to 5 megawatts of pilots with clear use cases. We can have a right context for each site. We can have a microgrid for coastal or island community for remote sites, and industrial anchor loads for round-the-clock reliability, and grid support nodes for predictability and grid balancing value. Now, these early pilots demonstrate reliability. They'll find out operation and maintenance cycles, and they will also estimate the cost curves, establish the cost curves. Then we can establish India's national tidal test center. We can create an analog of EMAC, European Marine Energy Center, that we have in Scotland at Orkney. It is a facility that standardizes testing, certification, environmental monitoring, and grid integration protocols. This is how Scotland cut costs and accelerated innovations. We can, and this is very important, introduce early stage incentives, use targeted mechanisms that de-risk first wave of projects, for example, CFD style, price certainty, viability gap funding, accelerated depreciation, and CAPEX support. These signal market seriousness and they will attract the developers. And we can run 2 twin pilots in parallel for faster learning. We can select 2 flow sites and demonstrate 2 distinct pathways, one for microgrid based pilot and one for a grid connected pilot. So together they prove that tidal's dual value, which is a local resilience and national grid integration. To conclude, tidal stream energy is predictable, scalable, and clean, which is a perfect complement to India's solar wind backbone. And Scotland's journey shows how to deploy them safely and bring the costs down. With focused pilots, a test center, and smart incentives, India can tap an estimated 12.46 gigawatts of potential, strengthening its energy security, reducing emissions, and building a more resilient grid. We are ready to partner from Scotland on water, in factories, and in policy designs. So thank you very much for your attention, and I'll be happy to take questions later on. Thank you.
Thank you, Mr. Ketan. Of course, in the mixed basket of power sources, tidal will surely play a role by 2035. Now requesting Mr. Dushyant Rathore, Superintendent Geophysicist Wells, ONGC. And he has got a total experience of 10 years and he is presenting on repurposing dry wells into geothermal assets.
Good afternoon all. My name is Dushyant Rathore and I am working in ONGC. In C-Well, basically, we are the petrophysical solution providers for conventional and unconventional wells. And actually, the basic idea, the repurposing of dry wells into geothermal energy. And this idea is, I am benchmarking with the well-established case of Hawaii, China. So let's see how this can be utilized in the energy domain, as we have seen the tidal energy and other energies, and how this untreated energy can be worked and can be utilized. Let's see. So what was my motivation? India's energy demand is increasing day by day, isn't it? And we are trying how we can meet these demands, either by the fossil fuels, by the energy, means in terms of every renewable source. So we have something hidden. What? Wells, oil and gas wells. When these are drilled, world over, thousands of wells are available, and after abandonment or dry, or after the taking all oil, means these are the marginal, when the wells are marginal, lots of our resources in terms of money has been sunk. So nowadays USA, China, Germany, Netherlands and other countries are repurposing these wells. Can't be used in this India. So study has gone beyond, and GSI has identified means megawatts, 10,600 for technical geothermal potential across 340 anomaly sites, means where we can drill these wells. And so drilling is a costly affair. It will take crores of rupees. So in my study, I have identified some areas, or we can identify other areas also, and we can repurpose these already drilled wells, and how we can do open loop or closed loop, and we can harness our energy. And this energy will be uninterrupted energy, means once we have gone this system, the energy will go up to 30 years, 40 years. So it's not interesting. So Um, uh, Means in our study, the technical side is we have three type of system: open loop system, coaxial or closed loop system, or hybrid two loop system. In open loop system, suppose a field is Gandhar in the western India. Here, what we can do, that lots of water, it means permeability is more, porosity is available. So in open loop system, we require a hot water. Hot water is coming, we can take energy from it, we can move turbine and generate energy. What in closed loop system, if porosity and permeability is not there, means in between the rocks, if water cannot move, so from where we can get energy? Then it comes the closed loop system. The pipe will like that. Okay. This is the from the one portion, the water will go inside, it will heat it up, and the outlet temperature will give us some temperature. The temperature will be enough to give us to generate the electricity or heat up for heating purposes. Hybrid loop system, if two or more wells is connected, then it grows, enhanced, and give energy. Capex benefit I have already discussed, that capex will be down approximately 50%. So in the hydro, as I discussed, in the hydrothermal open loop, this can be used in open loop system, where fluids circulate openly through naturally occurring fractures. In closed loop system, in my study, I am going to show you where in the Mandapeta we can use closed loop system and enhanced geothermal system. In some sense, exactly in Mandapeta, we don't have permeability. But if suppose we are getting some permeability or some good fractures, so we can integrate also this in the enhanced geothermal system and we can get energy out of it. So there is also technologies where we can enhance our means efficiencies. Means in closed loop system, nanofluids integration can be integrated in a pipe where Al2O3 means copper based, aluminum based, some micro nanofluids can be put and it enhance the energy efficiency. And study shows that 10 to 25% of energy can be enhanced. So engineered thermal boosters for geothermal system is the main central idea, and it is used in closed loop system, and it has been demonstrated all over the world how thermal enhancement can be achieved. Sir, I have selected field as Mandapeta as a pilot study, and here I have seen that the bottom hole temperature is more than means 110 degrees centigrade. It is enough, and it is going even more than 130 degrees centigrade, as I will show. And global analogy show that in Hubei oil field, China, it is also oil field where the same temperature regime has been utilized to produce the means in the low enthalpy water system, the same temperature regime is means giving the electricity generation 400 kilowatt per well, and using existing wells eliminates the drilling cost and subsurface risk. So in Mandapeta field is a very means explored field of ONGC. Here we have everything, extensive studies like all geological data, geosurface data, okay, heat flow estimate, extensive data, and so this can be repurposed. As we can see here, this is the depth domain and this is the BHT, Bottle-Horn temperature. Here the temperature is going up to 150 degree in average, 140, 130, means this regime can be directly utilized, and technology can be closed loop system, and normal fault regime means all geological studies is available here. So in our study, the reservoir and log reservoir and integrity assessment has been done. Here integrity assessment is validated through CBL, cement bond log, and variability density log measurement. Actually the rock works like a infinite quasi source of heat. So it is giving heat all along the time. If the behind the casing, if the cementing will be perfect, then the heat conduction will be proper. So it is a very important means in this particular project we need to see the well stability and the integrity. The second slide is lithological addition through petrophysical evolution. Thick sands is very important, so it can conduct the heat. And the other one is internal and external integrity failure, where the pipe is or tubing means casing is integrity is perfectly in the situation or not, and the reservoir pressure, that is the fourth one, where means in geological situation it is it not falling in an active fault zone or the well stability. So these stability of the well study and the condition and the integrity assessment as the main purpose, and this data we already have. So Hawaii oil field I have discussed. This is the main our benchmarking field, and here we can see the temperature is in our same as the Mandapeta, and the depth is regime also same, and this is the geological information. The map is showing that it is not in the very means the heat temperature gradient is not too much. This is the purpose of showing this map. So finally, in environmental integrity, it will produce low means ultra low emission. Water surface protection will be there. Minimum land footprint, as we have already drilled wells and we are utilizing these wells, and operational environmental controls as standard ramp protocols. So no environment will be harmed throughout, means minimal environment will be harmed throughout this our geothermal project. And what are the key takeaways for the Mandapeta field? Yes, we have resource confirmation, reuse of wells unlock immediate advantage, and capex will be means lowered up to the 50%, as studies shows. We have enough analogy and geological studies for sedimentary basin, and technology is already available. It is the opportunity to India to take up the challenge and further move to fulfill the energy demand of the country. World over, several studies shows this repurposing of wells is providing continuous energy to the nation as closed loop and loop system. In the ONGC, we have plenty of basins. In the, if you see the scenario of total country, there are hundreds of wells available. There are some of the means many of the wells are marginal today, and we can make utilize again. So as we say na that waste to energy. So this is a perfect example of waste to energy. So I give a special thank to IEW in India Energy Week team. My heartfelt thank you to ONGC management and CWEL for continuous support. Thank you.
So our last session for this waste to energy session is by Mr. Mahesh Kasture. He is the Chief Manager BPCL and 25 years R&D experience on nanomaterials, catalytic materials, plastic waste recycling and circular economy. So welcome Mr. Mahesh. He is presenting on novel photobioreactor technology for municipal liquid waste treatment.
Thank you very much, ma'am. Thanks a lot for introduction. As the topic is very relevant to us, and as our chair has started the discussion that what is most important nowadays is the waste valorization. So we have to extract the value from the waste, because we cannot afford the waste to let on the road or somewhere else. That is creating a problem for us. So this is a small case study that I am going to present to you. A joint collaboration, how a small thing can be taken up to the pilot scale and how we can take the benefit. As you are aware that the next important thing that is going to come is a water, and water circularity is one of the most important topic that probably going to discuss in near future. So with this, we have joined hands with Institute of Chemical Technology, and Institute of Chemical Technology has developed ALJ, and I'm happy the scientist who developed, Professor Kulkarni from ICT, is right here with us. The objective was that the water that we are using in our colony, can we take the part of that water out, treat it with this novel technology that has been developed by ICT, and can we put back into the use, may not be for potable use, but at least for the general use. Maybe for the garden purpose or maybe for other purpose, normal purpose. Can it be done? So with this particular technology, we have started using this ALJ developed at laboratory scale. And the result developed at laboratory scale has gave us a confidence that yes, this material is working properly. So after getting some good result at laboratory scale, we have scaled up the process to just 1 KL level at ICT. And we have used this algae that has been developed locally. As you know, basically this is Centesmus obliquus is known for consuming CONO, SO and PO from the water. However, there is no process at pilot scale is developed with this particular algae. So this is for the first time that we got this success at 1 KL level. And with that, then the parameters to design to scale up at least a pilot level scale has been done at ICT. What was important is that the initial parameters such as the design of the tube, optimization of a contract time to get a desired result, that has been done at ICT. And based on this optimization, a large scale photobioreactor at pilot scale has been worked out with Bharat Petroleum. As I have already mentioned that the results that untreated water and the treated water with the existing technology developed, that we have cross-checked, and we found that there are substantial reduction in the parameters as per the CPCB standards, because that is the minimum thing that we have to meet if you would like to take this water out. So once we have those parameters optimized and our algae parameter, flow rates, everything has been optimized at laboratory scale, we moved up to the bigger scale. So this is the layout that the plant which is currently in operation. It is about 6,500 square meter area and there are about 900 tubes. And each tube is having about 50 liter capacity. So this plant, we have taken 1/5 of the quantity of the water that has been coming out from our colony waste. This water has been stored in a store tank, and with the gravity this water has been fed using the algae developed by ICT. So initially we have spent about 4 to 6 months to understand how the process is going on. There where again we did fine tuning, and after doing fine tuning, the final process has now been operational since almost last 6 to 7 months. And we are getting the results, the desired results, and the water is now in use for certain local purposes. So as I mentioned, basically the process is this, that we are collecting the sewage water, subjected it to the algae treatment through these tubes. There are membrane filtration. These membrane filtrations will take this algae out. The algae that has been utilized, that we have to take it out, that we are taking it out. And the water that has been obtained will further subject to the usage. And the algae that is obtained, that can be either used as a fertilizer. Right now we are using it as a fertilizer for our local garden purpose. However, further this algae can also subject to oil, and we can extract some oil and we can further utilize, convert it into energy. So that is MSW valorization, that can also be done. Right now we are using it as a fertilizer. So this is the typical process flow that currently the plant is operational. This is a complete SCADA based system. So all the parameters we are monitoring online. We are getting COD, POD parameters on a regular basis, and the water quality has been monitored as per the parameter as per the approved parameters, and then we are releasing this water for normal usage. So this is the plant that you can see the overall plant on first figure, and secondly we have the aerators through which we are taking this air has been purged and the dissolved CO2 has been utilized for this photobioreaction. So you are utilizing CO2 also from the atmosphere. This is a 24/7 cycle, so you can see the two photographs, the plant in daytime and night time. We have made a provision of a lighting, so this plant is 24/7 operation. So the parameters of water we are measuring on periodic basis. So every 3 days or every 4 days, whatever water this plant releases, these parameters are being tested. And you can see the discharge, the effluent discharge is about, as per the parameter, it is less than 250 COD, less than 250. The pH is also well within the range, and that is meeting all the criteria as per the BIS standards. So the salient feature of this is generate about, it's a this is a 2 lakh liter per day capacity plant. Generate about 40 kg of algal biomass per week. This algal biomass that we can further utilize for agriculture, as I have mentioned. Since this is a pilot, initial capex is about 6 CR, and all the parameters of water that is treated, that has been optimized, and the plant, as of now, the plant is operational successfully since commissioning. The accomplishment is that we have already set the limit. Unless and until the COD comes down below 250, it will not be released. So this parameter has been stringently monitored. So the overall cost saving on water basis, whatever water that we are getting is about 81 lakh. However, I would like to mention that we are still observing this. This is under examination, and the further economic calculations will be done. And as I have mentioned that the water that has been aerated through these tubes, the CO2 has been utilized for the process. So the estimated quantity of CO2 is about 5.8 ton per year when the plant operates at its full capacity. So this is the first pilot-based 0.2 MLD plant that has been commissioned based on this process. Of course, this has won the award also. And expression of interest from some other parties has also already been asked, that some party has shown keen interest in implementing this process in their campus, at least for pilot scale. Thank you very much. Thanks a lot for your attention. Thank you very much.
Yeah, so I think we'll wrap up the session here. Thanks all the participants for wonderful presentations, and to the audience for patiently listening, everyone. Thank you.